This is part 2 of the Introduction to Electricity, section 1.2.2. This section mainly covers Ohm's law and how the resistance in a circuit is directly related to the volts and the current. If we look down here, we see that voltage, we use the letter V for its abbreviation. We talk about it in volts. And the symbol that is used is V when we're talking about how many volts something is. Current, the abbreviation we use is I. We talk about amps, and then the A is the symbol that we use that stands for amps. Resistance, the abbreviation is R. We talk about it in terms of ohms, and the Greek letter omega is the symbol that we use. So when I'm solving, or when I'm dealing with Ohm's law and I'm looking for one of these three unknowns, V equals IR is the actual formula for if I'm looking for voltage. I equals V divided by R if I'm looking for my current, and R is equal to my V divided by my I when I'm looking for my resistance. Easier way to think about it, this is a circle. I've also used just a T-chart where this is the top of my T, this is my leg. To solve for V, I cover up V, and then I have I times R. If I want to solve for I, or my current, I cover up I, and then it's V divided by R. If I want to solve for R, I cover up R, and then it's V divided by I. An example of Ohm's law, we have a flashlight that has a 6-volt battery and a resistance of 150 ohms. I want to know how much current will be drawn when I turn on the flashlight. So if I'm looking for current, first of all, here's my schematic diagram. I'm looking for current, which is my I sub R. So I cover up my I, so I have V divided by R. So 6 volts divided by 150 ohms gives me 0.04 amps, and when I convert that to SI notation, it's 40 milliamps. We have two main circuit configurations the only two you ever really see, or every circuit configuration is made up of these two. We have series components that are connected end to end. There's only that one single pathway for current. Parallel circuits, you have both ends of the components are connected together and there are multiple paths. Keep in mind, parallel circuits have these parallel lines. Really easy to remember parallel circuits. Something that stands out in series circuits that I'm going to say numerous times. Series circuits, the voltage changes from component to component. They call it a voltage drop. When I add all the voltages together, it gives me the total voltage into the circuit. The current does not change in a series circuit. In a parallel circuit, my current changes from drop to drop, or from component to component, but my voltage does not change. Kirchhoff's voltage law, which I stated just a little bit ago, is that if I add all the voltage drops, or all the different individual voltages at each of the components, it equals to the total applied voltage, or the total voltage put into the circuit. Kirchhoff's current law, and this one only works for parallel circuits, is that if I add all the individual branches, or all the individual currents at each of the components, it equals my total current going into the system. Series circuits, this is one way to look at it. If I take out one light bulb or take out one component, all of them go off. Here's some formulas for series circuits. The current flowing through every series component is equal. I said that already. Say it again. The current going through every series circuit is the same at each and every item. The total resistance is equal in a series circuit to the sum of all of the resistances. And this is how you verify Kirchhoff's law. If I know the total current, if I know my total voltage, I find my voltage at each of my components using Ohm's law, the V equals I times R, and then if I add all of those voltages up, it should give me 12. Here's an example of a series circuit. We'll just go through this one rather quickly. I want to find the total resistance. To do that, I add the resistances in each of the individual components. 1.2 kilo ohms is the same as 1200 ohms. That's how we have to think of it. So it comes out to 1900 ohms. When I convert that to SI notation, it's 1.9 kilo ohms. To find the current going through each component, I use Ohm's law. I'm looking for I, so it's V divided by R. If in this case we're looking at the entire circuit, since the current's the same through the entire circuit, so those are our T's. So to find the total current in this system, I take my total voltage, which is 12 volts, and I divide it by my total resistance, which was 1.9 volts, or 1.9 kilo ohms, or 1900 ohms, and I get a total of 6.3 milliamps. That's after its conversion. And since this is a series circuit, I know it's the same in every component. The current's the same. To find the voltage across each component, I'm solving for V. So V equals I times R. So I take on the first component, so voltage at resistor 1, my current there is 6.349 milliamps, and I multiply that times my 220 ohms. Keep in mind, before I do any multiplications, I must always convert this 6.349 milliamps into regular amps, which would make it 0.006349. I do the same at resistor 2, and I get a total of 2.984 volts, and the same at resistor 3, and I get 7.619 volts. To verify Kirchhoff's law, I know that the total voltage should equal the addition or the sum of all of my voltage drops. I add them all up, and I get right at 12 volts. Parallel circuits, a good way for you to see how this is. If I pull one component, only that branch loses power. The other branches continue to get power and continue to run. Some characteristics of a parallel circuit. As I said before, the voltage across every circuit is the same, but the current changes at each individual branch. Total resistance is equal to the reciprocal of the sum of the reciprocals, which is a really nice way of saying that this right equation here is the one that we use. So I put in my resistance value for all three of them. I sum up the fractions, and then I do some more fancy math in a calculator, and it gives me the total resistance. In the case of parallel circuits, Kirchhoff's current law is the one that we use to verify, and that just means that I add up all the current from each individual branch, and it should equal my total current. Here's a sample or an example parallel circuit that we'll go ahead and find all these different items for. So the total resistance, to find that, I take 1 over each of the individual resistances that you see here. Keep in mind that before I can do any sort of calculations, I have to convert these SI notations to standard notation. When I do that, I get 350 ohms, or right at about 350 ohms. To find the voltage across each component, I know that this is a parallel circuit, so in parallel circuits the voltage is exactly the same in every circuit. To find the current through each component, I use Ohm's law, so I take my total, to find my total current, I take my total voltage, since it's the same in every single one of them, and divide it by the resistance at that value. So at resistor 1, I have 15 volts divided by 470 ohms, and I get a total of about 32 milliamps. I do the same at resistor 2, and I get about 6.8 milliamps. And I do the same at resistor 3, and I get 4.5 milliamps. The total current should be equal to the total current we found previously for the total. So I take my total voltage, divide it by my total resistance, and it gives me the same as if I were to go and add all of my individual currents together, and they're almost identical. When looking at combination circuits, what happens if I remove light 1? The entire circuit goes out. If I remove light 2, 1 and 3 are still burning. If I remove 3, 1 and 2 are still burning. Electrical power we measure in watts. Power is equal to current times voltage. You deal with this a little bit more in section 1.2.5 or 1.2.4, right around there, when we really start talking about work, energy, and power. So keep in mind that power is equal to current times your voltage, and we measure that in watts.